In this section, we're going to look at some other identities that we can use to rewrite formulas in exact form, even if they're not our normal angles like 30, 45, and 60. Here are our double angle formulas, and we see the fact that they're double angle formulas because it has the sign of 2x. So that means that whatever we're taking the sign of, it has been doubled, and then we have on the other side of the equation, we have them rewritten in terms of just x and not 2x. You can see in all of these, we just have an x, we don't have 2x. We're going to use this to try to rewrite some statements, finding the sign of double an angle. So here we're given the cosine of theta is negative 3 over 5. And we're told that theta is in the second quadrant. So if we draw this out, second quadrant, all we know is that theta, cosine of theta, whatever our theta is negative 3 over 5. So that would be adjacent over hypotenuse, so negative 3 over 5. This tells me this is going to be a 3, 4, 5 triangle. Those always work out to be those numbers there. And so that'll give us some of the other sides here that we can use to find the following expressions. So we'll start off with sine. And actually, before I do that, we're told cosine of this theta is negative 3/5. Sine of theta then would be 4/5. And tangent theta would be opposite over adjacent, so negative 4/3. So with A, we're wanting to rewrite sine of 2 theta. Let's take a look at the identity that we had there. We saw that sine of 2 theta is equal to twice the sine of x cosine of x. So we're just going to write that 2 sine theta cosine theta. Well, we know that sine theta was 4/5, so that's going to be 2 times 4/5 multiplied by cosine of theta, which is negative 3/5. So that gives us, let's see, just multiplying the fraction, this is going to be 2 times negative 12 over 25. That 2 goes up with the 12, so that gives me negative 24 over 25. If we think about the fact that the angle is in the second quadrant, and we were doubling that angle, when you've barely gone into the second quadrant there, like you'd be at like 91 degrees, right? But if it's at 90, if we doubled that, that takes us to here, right, to the other side of the x-axis, to pi. And so anything under that is going to take us into or anything over that would take us into the third or the fourth quadrant, because if we go all the way to pi and double that, that would take us to 360. But regardless, you'll notice that sign here was negative, and anything in the second quadrant is either going to take us into the third quadrant or it's going to take us into the fourth quadrant. And in both of those quadrants, sine is negative. All right, let's do the next one there, cosine of 2 theta. And going back, we can see that the cosine 2 theta, this is one of the first ones they give us, but they actually give us 3 different ones. So we're going to do at least 1, maybe 2 of those. Let's start with the cosine squared minus sine squared. All right, again, let's write down we're in the second quadrant. And it was negative 3/5, and this is 4/5. cosine was negative 3/5. Sine theta was 4/5. And tangent theta was 4/3, and that was negative. Okay, so cosine squared then is negative 3/5 squared. And we're going to subtract from that sine squared, which is 4/5 squared. So that gives us 9/25 minus 16/25. And 9 minus 16 would give me negative 7/25. So our cosine there, or our cosine doubled, is negative 7/25. Let's see if we get the same thing, cosine 2 theta, with one of the other ones. And I'm going to go with the 1 minus sine squared theta. And we know sine squared theta, or sine theta, is 4/5. So we're going to square that. So that's 1 minus 16/25. 1 we would rewrite as 25/25, so they have the common denominator, minus 16/25. Did I do this right? And I see where my mistake is. This was 1 minus 2 sine squared theta. So we got to put a 2 there. So that's 1 minus 2 times this. I'm going to put 2 over 1. And that's going to adjust that second thing. We're still going to put 25/25 for the 1. But 2 times 16 is 32. And now this works out the way we expected it to. 25 minus 32 is negative 7/25 as well. So we see that works out with the cosine. And we have lots of choices. We have this one, we have that one, and then the third one was using cosine as well. And one of these may be more palatable than another. If you're given a sine and you're asked to find the double angle there, you're given sine, so then you're not having to worry about finding cosine of x. Or if you're given cosine of x, like we were in this case, we could jump right to this formula for that. All right. Let's go now to the tangent of 2 theta. Tangent, if you recall, our tangent of theta was equal to 4/-5, so negative 4/5. And I just want to double check. I think that's what it was. No, it was, I'm glad I checked, 4/3. So let's fix that. Now let's see if we can get a simplified result here. So this would be 2 times negative 4/3 over 1 minus negative 4/3 squared. So on the top we get negative 8/3, multiplying 4/3 by 2. And on the bottom we have 1 minus 16/9. And getting a common denominator, 9/9 for my 1. 9 minus 16 is negative 7/9. Multiplying the top by the reciprocal of the bottom, we'll take negative 8/3, change this to a multiplication, and flip that second fraction. 3 can go into 9, so that simplifies, but 3 doesn't go into 7. So we're left with negative 24/7 for my tangent of 2 theta. So how did we get the double angle formulas that we're looking at? And before I go into this finding a triple angle formula for sine, I want to just take a step back and let's take a look at sine. And if we have double an angle, in other words, 2x, which is what we had before, we could re-express that as x plus x, right? X plus x is 2x. And so this is putting it in terms of the sum and difference properties that we were looking at. If I use the sum and difference, if you recall, this gives me sine x cosine x. The signs match up, and we get cosine x sine x. Now, normally, those are different angles, right? We had the u and the v. But if they're the same angles, you'll notice that with products, we can express them in any order. So these are essentially the same thing, sine x cosine x plus sine x cosine x. All I did here was switch the order of the second one, just so we can see that these are actually like terms. In other words, what we have found is 2 sine x cosine x. And in fact, this is the double angle property that we were looking at. So if we apply this same logic to get a sine 3x, I could take sine of 2x plus x, and we can apply that same property here. Stretching this out, this would be 2 well, no, I'm sorry. We're going back to not 2, but sine 2x cosine x plus cosine 2x sine x. The one we're trying to validate here is this one. So we want to keep, just like when we were doing proofs, kind of keep our eye on that. We want them both in terms of sine, because there may be other ways to express these. I'm mainly concerned about this part here because remember we had 3 different formulas we could use for cosine of 2x. Let's take this to a different screen. So keeping our eyes on what we're after here, we know we want a statement that involves a lot of signs. And so we don't have a lot of choice with this part here. That has one identity that goes with it. So we're going to go ahead and put that in and rewrite this. This would be 2 sine x cosine x. And then we're multiplying it by this, another cosine x here. And I'm going to leave that for now, but I basically just substituted in the double angle formula to get this. On the other side, I have some choices. And this is where I was alluding to with cosine. We have choices of what we can substitute in there. And since my final statement needs to be made up of signs, to me, the most logical substitute we could put there would be the one that involves only signs, which is 1 minus 2, don't forget that again, 2 sine squared x. And then this also is multiplied by another sine of x. And in fact, since this involves a difference, right, so we have a subtraction there, this sign needs to be multiplied. So I need to put parentheses around this because I'm going to want to distribute this. Again, just trying to simplify this out. So let's rewrite this. Here I can combine these two. It's cosine times cosine. So this is 2 sine x times cosine squared x plus sine x. My sine x times 1 gives me sine x minus 2 sine to the third x, which I'm looking here, I'm noticing, okay, there's something here that I'm getting close to, right? A sine cubed x. Now, the one thing, again, that I want to be able to get rid of, if I can, or rewrite is this cosine squared x. I don't want a cosine in my final statements, right? My final identity here. So can I rewrite that in terms of x? In terms of sine. Can I convert that cosine into a sine somehow? And if you remember the Pythagorean theorem, cosine squared x plus sine squared x is equal to 1, cosine squared x can indeed be rewritten as 1 minus sine squared x. And that'll be good because I want to get rid of a cosine. I don't want any cosine. So that's 2 sine of x. And we'll substitute out the cosine. Whenever you do substitutions like that, it's always a good idea to put parentheses and then slug them in there. This will keep you from forgetting to distribute if you need to. That was the same thing that we ran up here. This is cosine of 2x. I wanted to subs that out for a 2-term deal. And that's important because cosine 2 of x is being multiplied by sine x. So whatever I substitute cosine 2 of x, whatever I substitute for cosine of 2x, that substitution needs to be fully multiplied by sine x. And so sine x has to go to both parts of that difference. All right, but we already did that, so let's just keep rewriting this here. So we have that's plus sine x minus 2 sine cubes of x. And now we're going to go ahead and distribute here. So that gives me 2 sine of x times 1, so 2 sine x, minus 2 sine x times sine squared of x, so 2 sine cubes of x, plus sine x. You can never write it too many times. All right. We have like terms now. If you'll notice, these two terms are like, and they would combine together to give me minus 4 sine cubes of x. And then I have 2 sine of x plus 1 sine of x. That gives me 3 sines of x. And that is what I was going for, success. I wanted to put this in terms of sine, and I did so. And in fact, I showed and proved that this could be a triple angle formula for sine.